So today we're going to be talking about different types of chemical reactions. In general, these are the 5 different broad categories for these reactions. Our first is going to be a synthesis reaction. Essentially, all you have for a synthesis reaction is you have 2 different elements. So we can say element A and then element B. And if I combine or I react those 2 different elements, I'm going to form a new compound that's just made up of those 2 different elements, like element AB. So, for example, we might have something like sodium metal, so Na. And if I combine that with chlorine gas, those 2 different elements are going to combine and they're going to form NaCl, or sodium chloride. So we started with our Na and our Cl separated. And then after the reaction, I have one overall compound. Our second type is going to be the opposite of that. So I might have something like, our general formula would be like AB, some kind of compound. And then after the reaction, those 2 will be separated. So let's say I have the same thing, NaCl, and that's going to break down back into our sodium, our Na solid, and our chlorine gas. So again, we started with one thing, and then that one thing turned into 2 things. Sometimes in decomposition reactions, you'll also see heat, because you have to think what's causing this thing to break down. So a lot of the times, you'll see something like this. And I draw my arrow. So you might have something like that, and then you might see a couple different things here on the other side of the plus sign for NaCl. You might see something that says heat. You might see a delta H. Those are 2 different options. Those are probably the 2 most common options I've seen. You could also see it written like this. CO2. So I could have also written it with a little arrow coming into this base arrow, and then I could write heat, or that delta H. Just means that I'm adding heat to this sodium chloride, and it's causing that to break down into 2 different elements. So these are 2 different kind of alternate versions that you might see as decomposition. For single replacement, now here we're starting to get slightly more complicated. So synthesis, decomposition, we only have 2 different types of elements, whatever A is and then whatever B is. For single replacement, we're still going to have our single element, but now I'm going to be combining it with 2 different elements that are already bonded. So some kind of element A combined with BC. And that's going to react. For single replacement, what we're looking at now is that our base element A is going to be coming in here, and it's going to be kicking out this element B. It's going to kind of substitute its spot. So I'll have A, C, plus B. So it's just kind of replacing that element. It's just a single replacement here. Double replacement, kind of like single replacement, now just 2 things are going to get replaced. So both elements are going to switch their partners. So I might have AB, and then CD. So now both are going to switch. So I know A is going to mix with D, so I'll say AD. And then my element B is going to mix with element C, so that'll be BC. Notice that the first element, element A, is going to bind with the last element, element D. That's because if we think about how things are written, like NaCl, generally when we do this, when we make chemical bonds, we saw that the first element is going to be less electronegative. And our second element, it's going to be more electronegative. For ionic bonds, it's really easy. We just talked about how the first element is like our positive charge. Our second element is like our negative charge. Same type of thing is going to happen with covalent bonds. It's just instead of like a full positive negative, you're going to have that slight negative or a slight positive. But for covalent bonds. But generally, that's kind of the format for this stuff. So let's say we write a double replacement, and let's keep this in mind and see if we can see why A and D would combine. And we'll take a look at some of those examples in a little bit. And finally, for combustion. For our combustion reaction, general formula is CX, HX, or HY. If that is in the presence of oxygen, and we add a little bit of heat, that's going to combust and form carbon dioxide and then water. Both of these should be in the gas phase. So general for combustion reactions, this thing that we wrote, this CXHY, this is just any hydrocarbon. Hydrocarbon, exactly what it sounds like. Anything that has hydrogen and carbon combined. So we're not adding anything else to it. It's like no halogens, no oxygen groups, just any number of C's and any number of H's. So this could be CH4, C2H2, C3H6, like any combination of those things. So these are going to be like the general formulas that you should know. That's going to be the general formula for synthesis. You start with two things, you make one thing. So thinking about like an ionic bond, right? Sodium plus chlorine, going to make sodium chloride. You should also know decomposition, so that's going to go in reverse. So you start with one thing, that's sodium chloride. With a little bit of heat, a little bit of energy, we can break those down into two different things. So it's kind of just the opposite. For single replacement, again, you start with one thing, and it's going to kind of kick out whatever else it's reacting with. And we'll see examples for that as we go on. And then double replacement, same kind of thing, but now both are going to change their partners. When you're swapping partners, just remember that the less electronegative, or the like positive pair, that's going to combine with the negative pair for the other. So if we come over here, this would have been like your positive, that would have been like your negative, positive, negative. So when we recombine, we need to take a positive, connect it with a negative. And that's why AD combines, your positive and your negative. Same thing with BC. B is your negative, C is your positive, so those are going to combine. B is your negative, positive, those combine. And then combustion, super easy way to see any hydrocarbon here. And then if you're in the presence of oxygen, you're always going to make CO2 and H2O in the gas form. So these are going to be your 5 different kind of base general formulas for types of chemical reactions. So let's take a look at identifying some types of reactions and balancing. So taking a look at this, I have CaCO3, and then after the reaction, so after that arrow here, I'm making CaO and CO2. So thinking about it, well, I see kind of just one group here, and then I'm turning it into 2 groups. So I'm looking for something that has, starting with one group, ends with 2 groups. And my only general formula that has that is decomposition. I start with that group AB, after the reaction, I have two different groups. So like this would be AB, that would be A, that would be B. So I know that this is going to be decomposition. So decomp. Now let's try to balance this reaction. In general, what I recommend people do when you're first starting out is to set up like a little table for yourself. So over here on my reactant side, my left side, I have Ca, calcium. I have a C, so I have carbon, and then I have this oxygen group, so I'm going to put O. And I'm just going to write down how many I have. So I have just one calcium. I just have one carbon. And then I have this subscript 3 that tells me I have 3 oxygens. So I'm going to do the same thing for the product side, the right side. So I should have the same elements, calcium, carbon, oxygen. And I can find those here. Calcium's right there, oxygen is right there, carbon is right there. So I have just one calcium. Easy, put 1. Next is carbon. I just have one carbon, nothing's connected to it, so I put 1. And then oxygen, I have 1 oxygen over here, and then I have 2 oxygens over here. So I have a total of 3 oxygens. So in this case, I have the same number of calciums on both sides, same number of carbons on both sides, same number of oxygens on both sides. So we're all balanced. So I can kind of just put number 1s all through here. So this one, super easy, already balanced for us. However, in our next example, we'll see that that's not always going to be the case. So here I have zinc metal, and it's going to be reacting with hydrochloric acid, and it's going to form zinc chloride and hydrogen gas. This was your ideal gas lab. So if I take a look at it, I have two things on my reactant side, on the left side. After the reaction arrow, my product side, I have 2 things. So if I start with 2 things and I end with 2 things, well, it could be single replacement, because I have 2 things, end with 2 things. It could be double replacement, 2 things, end with 2 things. Or it could be combustion, start with 2 things, end with 2 things. So it could be any of these 3. So let's kind of go down the list. Let's start with combustion. Combustion says any hydrocarbon plus O2 gas on the reactant side. Well, I don't see any hydrocarbons here. I don't see O2 gas. That means it cannot be combustion. Let's start with double replacement. I should have 2 different elements for both of my pairs. So I should have like an AB and a CD. Well, for this ZN, it's a single element, so it would just be like A. This hydrogen would be like B. Chlorine would be C. So because ZN is by itself, I know that it's not double replacement, and it has to be single replacement. Kind of matches that, right? A plus B, or A plus BC. I have my arrow. Well, now here, ZN was A, Cl was C, and then H was B. So it looks like A is kicking out B. So yeah, this is definitely going to be a single replacement. I'm just going to put SR for single replacement. So let's go to the same process for balancing this equation now. I have on my reactant side, my left side, I have Zn, I have H, I have Cl. Well, Zn here, there's no numbers touching it, so that means I just have one of those. For my H, no number touching it, so that just means I have one. Cl, again, no number touching it, means I just have one. Taking a look at my reactant side, we'll go through the same process. Zn, no number touching it, just 1. Cl has that little number 2 there. So that means I have 2 Cls. This H has this little number 2 here. So that's subscript 2, tells me I have 2 H's. So now that I have this set up, I see that I have the same number of Zns on both sides. I have 1 for both. But now for my H's, I have 1 on my reactant side, but 2 on my product side. So I got to figure out a way to balance that. When we talk about balancing chemical reactions, only way we can do that is with these lines. So we can add a coefficient, and we'll add a little note. Coefficient, just like in math, tells you how many you have. Essentially, what we're going to be doing is multiplying. So let's say, for example, that I have H2, right? Well, when I write H2 like that, what I'm really saying is that like a hydrogen is bonded to another hydrogen. Well, what happens if we take this H2 and then I put a number 2 in front? Well, what that means is I still have this base H2 molecule, but now this number 2 in front says multiply that molecule by 2, that you have 2 of those. So I have this H2 molecule, and I have this new one now. So that's all adding a coefficient means. A little shortcut, if I was just trying to figure out how many H's I had in total, I take my coefficient 2, multiply it by the subscript, and I do 2 times 2, and it tells me I have 4 H's in total. And if I check, 1, 2, 3, 4, 4 H's. So let's come back over here. I need to figure out a way to double the number of H's I have. So if right now I only have 1 H, I can think about this like a subscript 1. Well, if I want to double the amount, I can multiply that number by 2, or I can add a coefficient of 2 there. So by doing that, I'm going to double all of the atoms there. So 2 times that H, now I have 2 here. And then 2 times this 1 Cl, because I have 2 of these molecules now, is going to equal 2. So checking my H's, well, 2 is here, 2 is here, that works. And then checking my Cl's, 2 here, 2 here, that works. So my subscripts, or my coefficients, would be 1 zinc metal, 2 hydrochloric acids, 1 zinc chloride or zinc dichloride, and then 1 hydrogen gas. So that's going to be balancing chemical reactions in kind of like a nutshell. So let's kind of go through a more realistic practice problem of something you would probably see. So we're going to do the exact same processes, but now it's going to be a little bit of a word problem. So here, we're going to be given the reactants, and we're going to have to predict the products. So iron metal, in the presence of oxygen, is going to react and form iron oxide. So let's kind of break these down really quick. Iron metal, we're going to say Fe. It's saying we're metal, so we're probably in the solid state. Is going to react. That's basically what the in presence means, of oxygen. So now we have to use our chemical bonding knowledge a little bit. I know that oxygen has 6 valence electrons, so it's not fully stable. Well, what would make oxygen stable is if it got 2 more electrons. So there's 2 ways we could do that. We could either take 2 electrons from something else or share 2 electrons. And we talked about how in the gas unit, that if oxygen wants to share 2 electrons with another oxygen, well, now they'll both get those 2 extra electrons. And this is kind of the form of oxygen gas, or O2. So even though it doesn't say O2, in the presence of oxygen, it just tells me, oh, it's going to be like oxygen gas, O2 gas. And we're going to react and form iron 3 oxide. So I know there's going to be an iron in there, Fe. I know there's going to be oxygen in there, O. The only thing is I don't know how many, or I don't know if I should put like a subscript. Like, I don't know if I should put 2 here, or if I should put 3 here, or if I should put 4 over here. Like, I don't know what numbers to put. So I'm going to show you a little bit of a shortcut on how to do that. So when I'm writing things out, I want to rewrite them in the corner over here. And I want to think about like what charges these things are going to have. When I say charges, I mean like how many more electrons do they need? So I know oxygen, we just talked about how it has a -2 charge because it wants 2 more electrons. So I'm going to put like a 2 on top. And then I'm going to think about iron. So if you look up iron on the periodic table, it's a transition metal, which means that it has multiple options when it comes to gaining or losing electrons. But in the question, it gives us a little bit of a hint. It says, hey, it's iron 3 oxide. So for transition metals, those Roman numerals are going to tell you the charge. So I know it's Fe3. If it was iron 4, then that would tell me, oh, that's Fe4 plus. But this was iron, this was iron 3, so I know it's Fe3. So now what I can do is, I know that when these 2 things are going to bond, their charges are going to balance out. So if I kind of like cross multiply, then I can say, oh, this iron has a +3 charge. There's 2 of those, so 2 times 3 gives me +6. This oxygen, with its -2 charge, well, if there's 3 of those, 3 times 2 is going to give me -6. And by adding these 2 up, I get 0, no charge. So I know that's going to be the balanced version. So I'm going to come over here. I'm going to put my 2, my 3. And that's a little bit of a shortcut to figure out what those subscripts are going to be. And I'm going to throw my state of matter right there. So now that we have it written, I want to see if things are balanced. So we're going to go ahead and check that. I'm going to set up my little table. I have Fe, O. There's 1 iron on my reactant side, 2 oxygens on the reactant side. And then on the product side, well, I have 3 oxygens and I have 2 ions. So, thinking about it, I'm going to try to balance the ions first. I have 1 on the left side, 2 on the right side. Well, easy enough. If I put 2 in front of Fe, then I get 2 on both sides. So, okay. Now I'm going to check oxygen. Oh, I have 2 on the left side, 3 on the right side. Well, there's no easy way to get up there. So if I think about my closest common factor, well, 2 can get up to 6 pretty easily. 3 can get up to 6 pretty easily. So I'm going to try to get these both up to 6. Well, I know 2 times 3, that's going to get me up to 6. And then 3 times 2, that'll get me up to 6. So now my oxygens work, but I changed things. Because I put that 2 in front of my product, it's going to multiply to everything. It's like, yeah, it's still going to be 2 times 6 over here for the oxygen, but now it's 2 times 2 for this iron, and that's going to give me 4. So now my irons don't balance out anymore. So now I have 4 on the right side. How do I get 4 on the left side? Well, instead of putting a 2 there, I'm going to put a 4 instead. So balanced reaction would be 4 irons and 3 oxygen gases is going to form 2 iron oxides. So that's what a more realistic example problem is going to be. Some kind of word problem there. We have to turn it into an equation. You balance that equation, and then you end up with your final product here. Now, if we're trying to figure out what kind of reaction this is, I have iron, single element by itself. I'm adding that to oxygen. It's a single type of element by itself. And I'm forming this iron oxide. I'm forming one thing. So A and B are combined. Well, if I start with 2 things, I end with 1 thing. With this general formula, I know this is going to be a synthesis reaction. So that's all of the new stuff. So all we're going to do is do a quick recap. So in general, when we talk about chemical reactions, we have this general formula, or this general idea. Reactants are going to form products. This little arrow we're doing in the middle, we're going to call that our yield arrow. So whatever's on the left, we call reactants. Whatever's on the right, we call products. In general, we have 5 different types of chemical reactions. The example we did, our reactants were Fe and O2, and those yielded our products. This Fe2O3, what we call iron oxide. So reactants, we already talked about what those are. We have these things that I'll do in blue. These numbers we put in the front, we call these our coefficients. Coefficients just tell you how many molecules. So that 4 in front of the Fe tells me I have 1, 2, 3, 4. 4 Fe's. The 3 in front of the O2 tells me I have 3 of those O2 molecules. So I have O2, O2, O2. And that 2 in front of the Fe2O3 tells me I have 2 Fe2O3s. When we talk about these little numbers, they're called subscripts. Our subscripts are just telling you how many of that individual atom. So where coefficients kind of apply to everything that coefficient touches, it's like that 2 applied to like this whole molecule. Our subscript only applies to whatever it touches. So that 2 touching the O2 means I have 2 oxygens bonded together. When I look at this Fe2O3, that means I have 2 Fe's and then 3 O's. So 2 Fe's and then 3 O's. And then we talked about this idea of balancing the equation. When we talk about balancing equation, all we're really trying to do is get the same number of atoms on both sides. The reason we're trying to do this is this underlying idea called law of conservation. Of mass. All that means is that if you have a certain number of elements on the reactant side, on the left side, after the reaction you should have the exact same number of elements on the right side. You can't create or destroy matter, you can only change it. So that's essentially our kind of introduction to chemical reactions.